Tonight, somewhere above your roof, the universe is quietly expanding, and our best measurements of how fast do not agree. One method, built from starlight, says 73. Another, built from the oldest light in existence, says 67. Two numbers, one universe, 4 years. Astronomers expected the gap to dissolve into some small mistake. Then the James Webb Space Telescope was turned toward the leading suspect, the most likely source of error, and found that the error was not there. A Nobel Prize-winning astronomer looked at the results and said, "We now face the real and exciting possibility that we have misunderstood the universe." Tonight, we will follow that mystery slowly, honestly, one gentle step at a time. What was measured, what Webb saw, and why an unsolved universe might be the most hopeful thing in modern science. So dim the lights, get comfortable. You do not need to remember a single number. Just listen and drift. Hello, and welcome. I am glad you are here tonight. Before we go anywhere at all, take a moment to arrive. Maybe you are lying down. Maybe the lights are already low. Maybe there is a fan humming somewhere in the room, or rain against the window, or nothing at all. Just the quiet weight of the evening settling around you. Whatever is there, let it be there. You do not have to fix anything tonight. You do not have to remember anything either. Everything I am about to tell you will still be true in the morning, and it will wait for you patiently, the way the sky always does. Now, before we begin, I want to make you a small promise, because the story we are following tonight deserves one. Everything you will hear in the next few hours comes from published science, from real measurements, real papers, and real people whose names you can look up tomorrow if you feel like it. Where scientists are confident, I will tell you they are confident. Where they are guessing, I will tell you they are guessing. And where nobody on earth knows the answer yet, I will simply say so, because, as it turns out, that honest little phrase, "nobody knows yet," sits at the very heart of tonight's story. This is not a story about an answer. It is a story about a beautiful, stubborn, wide-open question. I think you will find that a question, told slowly enough, can be far more restful than any answer. So here is the whole mystery, in one quiet image. I want you to picture 2 clocks. Imagine a long wooden hallway in an old house at night. The floorboards are dark and smooth. The air is still, and on opposite walls hang 2 clocks. They are both beautiful. They were both built by master craftsmen who checked their work again and again, for years, with a care that borders on devotion, and they disagree. Not by much. That is the strange part. If one clock said it was 3 in the afternoon and the other said midnight, you would laugh, shrug, and assume one of them was broken. But that is not what is happening in this hallway. One clock reads the hour just slightly later than the other. A small difference. A polite difference. The kind of difference you would expect to vanish the moment someone competent came along and adjusted a gear. Except people have been adjusting the gears for years now. And every time they finish, the 2 clocks disagree again, by the same small, polite, immovable amount. At some point, a quiet and slightly dizzying thought begins to creep down that hallway. What if neither clock is broken? What if both were built correctly? And the problem is not the clocks at all? What if the problem is our understanding of the house itself? Hold that image gently, because those two clocks are real. And now I want to tell you, carefully, what each one actually is, because they are not quite twins. And the difference between them matters for everything that follows. The first clock is a measurement. It is made of starlight, of exploding stars, and the steady rhythms of distant suns. And it directly measures how fast the universe around us, the relatively nearby universe, is expanding right now. Tonight, we will spend the next 2 chapters learning exactly how it works. And you will meet the remarkable woman whose quiet discovery makes it possible. The second clock is different in kind, and this is the subtle heart of the whole mystery. It begins with the oldest light in existence, a faint glow left over from the infancy of the cosmos, a kind of baby picture of everything. Astronomers read that picture with exquisite care, and then they do something bold. They take our standard model of cosmology, the accepted recipe and rulebook of the universe, and they wind it forward. From that infant moment across nearly 14 billion years, to calculate what the expansion rate today should be. So the second clock is not a direct measurement of the present. It is a prediction of the present, built from the deep past, plus a theory. If the measurement and the prediction agree, the theory is working. If they refuse to agree, then either a measurement is subtly off, or the theory, somewhere, is missing an ingredient. And they refuse to agree. The measurement says about 73. In units we will make friendly later tonight. The prediction says about 67. Scientists call this disagreement the Hubble tension, and it has become one of the most closely watched problems in all of physics. It sounds like something a doctor might mention at a checkup, and that is not a bad way to think of it. A persistent symptom, the one reading on the chart, that refuses to come back normal no matter how many times the test is repeated. When the gap first emerged clearly, many researchers suspected the explanation would be ordinary. Someone, somewhere, had made a subtle mistake. A telescope slightly miscalibrated. A type of star slightly misunderstood. Dust in space, dimming distant light in a way nobody had accounted for. These things happen in science all the time, and there is no shame in them. Finding those quiet little errors is most of what real research actually looks like. So the reasonable expectation was that better instruments would tighten the gears, and the two clocks of the universe would drift back into agreement. That is where the James Webb Space Telescope enters our story. Though I want to introduce it honestly, Webb was not built to referee this one argument. It is a general observatory, 3 decades in the making, designed to study everything from the first galaxies to the birthplaces of planets. But its golden infrared eyes happened to be exactly the instrument the argument needed, because they could recheck the most suspected links in the chain with a sharpness no one had ever had. So when Webb began its work, teams of astronomers turned it toward the measurements everyone doubted, half expecting to watch the famous tension quietly dissolve. We will spend much of tonight walking toward what Webb actually found. So I will not rush it here. I will only say this. The most likely mistake, the one nearly everyone had been waiting to find, was not there, and the mystery, instead of closing, deepened. And this is the moment where a real human being steps into our story. Someone we will come to know well in the hours ahead. His name is Adam Riess. He is an astronomer at Johns Hopkins University, and in 2011 he shared the Nobel Prize in Physics because years earlier he and his colleagues had discovered something nobody expected, that the expansion of the universe is speeding up. He has spent much of his life building and rebuilding the first clock, the measurement, refining it, doubting it, and testing it again. He is, in a very real sense, one of the master clockmakers in that hallway. And, as the newest, sharpest observations kept refusing to line up with the prediction, he began to say, in official statements and published papers, what the data seemed to be suggesting, that we may have to consider the possibility that our model of the universe is incomplete. Later tonight, in its proper place, we will hear his actual words from the record, with their sources. That is part of the promise I made you, and I intend to keep it. For now, in this first quiet chapter, I only want you to feel the shape of the mystery, because it is a gentle shape, and it fits nicely in a dark room at the end of a long day. Somewhere out there, the universe is expanding. Every distant galaxy is drifting away from every other one. Slowly, calmly, the way breath leaves the body, we have one magnificent way of measuring that expansion, and one magnificent way of predicting it. And after years of checking, the two still give different answers. Maybe you already feel the pull of the obvious question. Which clock is right? It is a fair question, and we will honor it. But let me offer you a slightly different one to fall asleep with, because I think it is the truer question, and the more peaceful one. What if the most interesting possibility is not that one clock is wrong, but that both were built well, and the house is stranger than we knew? Here is our path for the night. First, we will go back about a century to meet the people who first taught us the universe is expanding at all, including a woman whose careful work with photographs of stars made all of it possible, though few people knew her name. Then we will climb, one careful rung at a time, the ladder astronomers use to measure the cosmos. We will visit the oldest light in existence. We will watch the two clocks emerge, tick by tick, and drift apart. And then we will follow the James Webb Space Telescope out into the dark to see what it saw. There is no test at the end. There is no hurry in the middle. If you drift off somewhere along the way, that is not a failure. Honestly, that is the design. Take one slow breath. Let your shoulders sink a little deeper. Down the hallway, two clocks are ticking, and neither of them knows yet which one the century will believe. To understand the first clock, we have to meet the people who built it, and that story does not begin with a telescope, or a genius at a blackboard, or a midnight flash of inspiration. It begins with photographs. Thousands and thousands of photographs of the night sky, printed on glass plates, stacked in wooden trays in a brick building in Cambridge, Massachusetts, at the Harvard College Observatory, a little more than a century ago. Each of those glass plates held a piece of the sky, frozen, thousands of stars on every plate, tiny dark specks on the pale glass, like grains of pepper spilled across a table. And somebody had to study them. Somebody had to measure each speck, compare it to the same speck on other plates from other nights, and write down, in careful ink, Whether that star had grown brighter or dimmer, it was slow work. It was quiet work. And at Harvard, at the time, it was considered work for women. They were called computers. That was the actual job title. Human computers. Decades before, the word meant a machine. The observatory hired women because they were regarded as careful and patient. And, it must be said plainly, because they could be paid far less than men. Records from the era indicate wages of roughly 25 to 30 cents an hour. They were rarely allowed to use the great telescopes themselves. Their world was the glass, the ink, and the endless counting. One of those women was named Henrietta Leavitt. She had come to astronomy almost sideways. First, as a volunteer, and an illness in her young adulthood had left her with a serious loss of hearing that deepened over her life. People who worked beside her described a person of unusual focus, someone who could sit with a magnifying eyepiece over a glass plate, hour after hour, in a quiet most of us would find unbearable, and simply see more than other people saw. Leavitt was assigned a task that sounds humble until you learn what came out of it. She was to study variable stars, stars whose brightness rises and falls in a rhythm, like a slow heartbeat in the dark. She focused on variables in two faint smudges of light in the southern sky called the Magellanic Clouds, which we now know are small neighboring galaxies. On plate after plate, night after photographed night, she watched thousands of these stars breathe, brighter, dimmer, brighter, dimmer. She found them by the hundreds, and became one of the great discoverers of variable stars of her era. And somewhere in that ocean of pepper-grain stars, she noticed something, a pattern, sitting there patiently, waiting for a person with enough patience to meet it. Among a family of variable stars called Cepheids, the bright ones blinked slowly, and the faint ones blinked quickly. The longer a Cepheid took to complete one pulse of its heartbeat, the more light it truly gave off. It was not a vague tendency. It was a clean, dependable relationship. And because the stars she was studying sat together in the same distant cloud, all at roughly the same distance from Earth, she could be confident the pattern was real and not a trick of some stars being nearer than others. She noted the relationship in 1908 and laid it out clearly in 1912 in a short Harvard College Observatory circular. Following the custom of the day, the circular went out under the signature of the observatory's director, Edward Pickering, but he stated in its opening line that the work had been prepared by Miss Leavitt, and the discovery has been credited to her ever since. The period luminosity relation. Some astronomers today simply call it the Leavitt law. Now, I want to slow down here, because if you carry one gentle idea out of this entire night, let it be this one. The hardest problem in astronomy, for centuries, was distance. When you look at a light in the dark, you cannot tell, from brightness alone, whether it is a candle nearby or a lighthouse far away. A faint star might be a small star close to us, or a giant star impossibly far. The sky is flat to the human eye. It keeps its depth a secret. What Leavitt found was a way to make certain stars confess. If a Cepheid's rhythm tells you how much light it truly produces, then you can compare that true brightness to how faint it merely looks from Earth. And the difference between the two tells you how far away it is. The slower the heartbeat, the brighter the bulb. Read the rhythm, and you know the wattage. See the faintness, and you know the distance. Astronomers came to call such stars standard candles, and the name is honest. Leavitt had found a candle whose label you could read from across the universe. She did not live to see most of what her pattern made possible. She continued her careful work until her death in 1921. There is a story, told often, that a member of the Swedish Academy began inquiries about nominating her for a Nobel Prize a few years later, only to learn she had already passed away. And the prize is not awarded after death. She never held the fame her discovery deserved. But her candle changed everything. And it changed it quickly. Just a few years after her death, a young astronomer in California named Edwin Hubble was studying a faint spiral smudge in the night sky. A smudge, many scientists insisted, was a cloud of gas inside our own Milky Way. In its glow, Hubble found a Cepheid, one of Leavitt's blinking stars. He timed its heartbeat. He read the label on the candle, and the distance that came out was so enormous that the spiral could not possibly sit inside our galaxy. It was a galaxy of its own, the one we now call Andromeda, an island of stars unimaginably far beyond ours. With that measurement, resting on one quiet woman's pattern, the known universe expanded from a single galaxy into a realm of galaxies, and Hubble was not working alone in history. So, let me widen the frame for a moment, because the next step had more parents than the textbooks used to admit. For years, an astronomer named Vesto Slipher, working patiently at a small observatory in Arizona, had been measuring the light of dozens of these spiral smudges, and had found something odd. In most of them, the light was stretched toward the red, the telltale sign of things moving away from us. And some were receding at astonishing speeds. And in 1927, a Belgian priest and physicist named Georges Lemaitre, working from Einstein's equations, proposed that space itself could be expanding, and connected the receding galaxies to that idea, publishing a version of the distance and velocity relationship 2 years before it made Hubble famous. When Hubble, in 1929, combined his Cepheid distances with those recession speeds, the pattern became unmistakable. The farther away a galaxy is, the faster it is receding. The relationship has carried Hubble's name ever since, though today many scientists call it the Hubble-Lemaitre law, in recognition of the quiet priest who saw it coming. The meaning took years for the world to absorb, and honestly, it is still absorbing it. The galaxies are not fleeing through space like frightened birds. Space itself is stretching, everywhere. Carrying the galaxies along the way, distant boats ride a widening tide. The universe is expanding, and the number that describes how fast, the exchange rate between distance and speed, came to be called the Hubble constant. That number is what both clocks in our hallway are trying to pin down. And notice what the first clock is truly made of. Glass plates, ink, patience, and the steady heartbeat of blinking stars, assembled by a woman earning 30 cents an hour, who was rarely allowed to look through the telescope. The first clock has begun to tick. A single kind of star, however faithful, can only take you so far into the dark. Cepheids are bright, but the universe is deep, and beyond a certain distance, even the most brilliant candle fades below what any telescope can see. So astronomers did what careful people always do when one tool runs out of reach. They built a ladder. They call it, quite literally, the cosmic distance ladder. Astronomers have invented many ways to measure distance. Radio beacons in orbit around black holes, pairs of stars eclipsing each other, the glow of the brightest red giants. And we will meet some of those methods later. But for the ladder at the center of tonight's story, the one behind the number 73, there are 3 main rungs, and I want to climb them with you slowly. Because the whole disagreement between the 2 clocks lives inside this ladder. If you understand it gently, everything that comes later tonight will feel like walking a path you already know. The first rung is the one grounded most directly in geometry, with almost nothing else assumed. Just triangles. The same mathematics surveyors have trusted for thousands of years. Hold one finger up in front of your face. And close your left eye. Now open it. And close your right. Do it lazily. No need to actually move if you are already comfortable. Just remember how it looks. Your finger seems to jump from side to side against the background of the room. Hold the finger farther away. And the jump gets smaller. The nearer the finger. The bigger the jump, your 2 eyes see the world from 2 slightly different places. And your brain uses the difference to judge depth. Astronomers do exactly this with stars. Except their 2 eyes are 2 positions of the entire Earth. In January, our planet sits on one side of the Sun. In July, it sits on the other side, roughly 186 million miles away from where it started. Photograph a nearby star in January. Photograph it again in July. And the star appears to shift, ever so slightly, against the wallpaper of more distant stars. That tiny shift is called parallax. And from it, with triangles, you can calculate the star's distance without knowing anything about how stars shine. The shifts are almost unbelievably small, which is why this works only for stars that are relatively close to us. But for those, parallax gives distances astronomers trust more deeply than any other kind. In recent years, a European space telescope called Gaia has measured these tiny shifts for more than 1 billion stars, giving the bottom rung of the ladder a firmness earlier generations could only dream about. Now comes the move that makes the whole ladder work. Among the nearby stars, whose distances we know from geometry, some are Cepheids, Leavitt's blinking candles, because we know exactly how far away those particular Cepheids are. We can put precise numbers on her pattern. We can say, a Cepheid with a heartbeat of this many days truly shines with this much light. The first rung calibrates the second. Geometry teaches the candles their own wattage. And once the candles are calibrated, they carry us outward. Find a Cepheid in a distant galaxy. Time its pulse. Note how faint it appears. And the distance to that entire galaxy falls into your hands. This is the second rung, and it reaches millions of light years into the dark, far beyond anything parallax could touch. But even Leavitt's candles fade eventually. Past a certain depth, no telescope can pick out one blinking star inside a galaxy of billions. So the ladder needs a third rung, a brighter beacon, and nature provides one. It is called a Type 1, a supernova. Here is the honest version of what that is, told at bedtime pace. Scattered through every galaxy are white dwarfs, the dense, burned-out cores of stars that have already died once, each one packing roughly the mass of the Sun into a sphere the size of the Earth. Left alone, a white dwarf simply cools forever. But white dwarfs are not always left alone. Some have close companions, another star, sometimes even a second white dwarf. And in certain of these partnerships, matters end explosively. The dwarf gains mass, or collides, or is detonated by a layer of stolen fuel igniting on its surface. And the details, I want to tell you honestly, are still being worked out. Astronomers are confident these events are thermonuclear explosions of white dwarfs, and they can see several plausible paths leading to the blast. But which path produces which explosion remains an active research question. One of those places where I promised to tell you when scientists are still guessing. So why trust such explosions as distance markers? Because of something wonderfully practical. However, they are triggered. The explosions turn out to behave with remarkable regularity. Each one brightens and fades in a pattern, a light curve. And in the 1990s, astronomers discovered that the shape of that pattern reveals the true power of the blast. Explosions that fade slowly are intrinsically brighter, in a precise, measurable way. And once you correct for that, and for dust, these supernovae become standardized candles of astonishing consistency. Not identical bulbs off a factory line, but bulbs whose labels can be read from their behavior. And they are bright enough to outshine an entire galaxy for a few weeks. Visible, not millions, but billions of light years away. And how do we learn the true brightness of these standardized flashbulbs? The same way as before. We catch them exploding in galaxies whose distances we already measured with Cepheids. The second rung calibrates the third, just as the first calibrated the second. Geometry teaches the Cepheids. Cepheids teach the supernovae, and the supernovae carry the measurement across the visible universe. That is the ladder. Parallax. Cepheids. Supernovae. 3 rungs, each standing on the one below it, each tended by people who have spent entire careers on a single rung. And this ladder is precisely how the first clock tells time. Astronomers measure distances to galaxies with it. Measure how fast those galaxies are receding from the stretch in their light. And dividing one by the other gives the expansion rate of the universe. Here and now. This is often called the local measurement, because it is built from the relatively nearby, relatively recent universe. It is Leavitt's clock and Hubble's clock. And in our era, more than anyone else's, it is Adam Riess's clock, because he and his colleagues have spent decades tightening every rung. But notice something, as you settle deeper into your pillow, something worth carrying into the next part of our story. A ladder is only as strong as its rungs, and every rung rests on the one beneath it. If the calibration of the Cepheids were off, even slightly, that small error would climb the ladder with us, quietly bending every distance in the universe. For years, whenever the two clocks disagreed, this ladder is where most of the suspicion pointed, somewhere on those rungs. Surely, a bolt was loose, and when the sharpest infrared eyes ever built finally opened, 1,000,000 miles from home, one of the first places astronomers aimed them was here, at these exact rungs. hunting for that loose bolt. What they found, and did not find, is waiting for us a few chapters ahead. Before that, though, we owe the other wall of the hallway a visit, because the second clock has nothing to do with ladders at all. It is built from a light older than the stars themselves, a glow that set out on its journey before there was a single galaxy anywhere. And that is arriving, faintly, at your rooftop tonight. Rest easy. The ladder will hold your weight while you sleep. The second clock begins with an accident, and with pigeons. It is 1964. In Holmdel, New Jersey, two young radio astronomers named Arno Penzias and Robert Wilson are working at Bell Telephone Laboratories, and they have been given a magnificent instrument, a giant horn-shaped antenna, originally built to catch faint radio signals bounced off early communication satellites. Penzias and Wilson want to use it for astronomy. And before they begin, they do what careful scientists always do. They test the instrument, to learn its quirks, to map every source of noise, so that whatever they eventually measure will be clean. And there is a noise they cannot get rid of. It is faint, a soft microwave hiss, the kind of thing most people would shrug at, but it's quepity that makes no sense. It comes from everywhere. Point the horn north. The hiss is there. Point it south. Still there. Day, night, summer, winter, toward the plane of the Milky Way or away from it. The same gentle hiss, always, from every direction in the sky at once. They check everything. They rebuild parts of the receiver. They chase down loose connections. At one point, they discover that a pair of pigeons has been nesting inside the horn, coating it with what an internal memo delicately called a white dielectric material. They evict the pigeons. They scrub the horn clean. Penzias told versions of this story for decades, with a kind of weary affection, because after every wire was checked and every surface polished, the hiss remained, everywhere, unchanging. What Penzias and Wilson did not know was that just a few miles away, at Princeton University, a group of physicists, led by Robert Dick, was preparing to search for exactly this signal, on purpose. Their reasoning went like this: if the universe began in an extremely hot, dense state, as the Big Bang theory proposed, then the light from that era should still exist. The universe does not have a drain. That ancient light would have been stretched by billions of years of expansion, cooled from a blinding glare to a faint microwave whisper. But it should still be here, arriving from every direction at once. The two groups learned of each other through a phone call, and when Dicker hung up, he is widely reported to have turned to his colleagues and said something close to, "Boys, we have been scooped." The discovery was published in 1965 in a pair of side-by-side papers, one from Penzias and Wilson, describing the hiss with almost comical modesty, and one from the Princeton group explaining what it almost certainly was. In 1978, Penzias and Wilson received the Nobel Prize in Physics. The pigeons received nothing, which historians of science generally agree was fair. That hiss is called the cosmic microwave background, and I want you to spend a slow moment with what it actually is. For roughly the first 380,000 years of its existence, the universe was so hot and dense that it was opaque, a fog of glowing plasma, light bouncing endlessly off free electrons. unable to travel in a straight line, the way light cannot pass through the wall of a furnace. Then the universe expanded enough and cooled enough for atoms to form, and the fog lifted everywhere, and the light that was in flight at that moment has been traveling ever since, in straight lines, for almost 14 billion years, growing fainter and redder and colder, until today it arrives as that microwave hiss, at a temperature of about 2.7 degrees above absolute zero. It is, in the most literal sense, a photograph of the infant universe, taken at the moment the cosmos first became transparent. And it arrives from every direction because the hot, early universe was not an explosion in one place. It filled every region of space, including every region from which light can now reach us. So its afterglow pours in from all sides at once. It is falling on your rooftop right now, in the room where you are lying, on some old analog televisions, tuned between channels. A tiny part of the flickering snow may even have included this ancient light. It is possible, in other words, that you have already watched a little of the universe's first morning, on a screen, without knowing it. Now, for a couple of decades after the discovery, the baby picture looked strangely blank. The glow was smooth, the same temperature in every direction to better than 1 part in 10,000. And that smoothness was actually a problem, because our universe today is not smooth. It is lumpy. It has galaxies and clusters and enormous empty voids. Lumps have to grow from seeds. And if the infant universe had no seeds, no slightly denser patches for gravity to gather material around, then nothing we see tonight should exist. The seeds were found in 1992. A satellite called COBE, the Cosmic Background Explorer, mapped the glow across the whole sky and detected them at last. Tiny variations in temperature, differences of about 1 part in 100,000, the faintest imaginable mottling on the baby picture. One of the mission's leaders, George Smoot, was so moved that he told reporters it was like seeing the face of God, a phrase that followed him for the rest of his career. He and John Mather shared the Nobel Prize in Physics in 2006 for that work. And those tiny, warm and cool patches were the seeds every galaxy you have ever heard of, including the one you are lying inside right now, grew from spots like those. Then came the era of reading the photograph seriously. A satellite called WMAP in the 2000s, and then a European satellite called Planck, launched in 2009, mapped those patches with breathtaking precision. And here is the gentle miracle. The pattern of the patches, their typical sizes, how strong they are at each size, is not random. It encodes physics. Sound waves were rippling through the plasma of the infant universe, and they left their fingerprints in that mottling. From those fingerprints, cosmologists can read off the recipe of the cosmos. How much ordinary matter, how much of the mysterious dark matter, how much dark energy, and how fast it was all expanding then. And here, at last, is how the second clock tells time. You take the baby picture, with all its measured detail. You take the standard model of cosmology, the equations describing how a universe with that recipe grows, azure, and expands. You wind the model forward, from the infant universe to today, like winding a film from its first frame to its last, and the model hands you a prediction. It tells you how fast the universe should be expanding right now. If the recipe is complete and the equations are right. Notice, one more time, how different this is from the first clock. The ladder measures the expansion here and now, directly, with candles and geometry. The baby picture clock starts 14 billion years in the past and extrapolates forward, trusting the model for every step of the journey. Two independent methods, different instruments, different centuries, different physics, different people. They share no rungs, no candles, no assumptions about stars, which is exactly why what happened next was so unsettling. In 2018, the Planck team released its landmark analysis, and the baby picture clock ticked out its prediction with exquisite precision. 67, and a little more. And on the other wall of the hallway, the ladder had an answer of its own. So now we can read the two clocks properly and see the disagreement with our own eyes. It comes down to two numbers, and I promised you that you do not need to remember anything tonight. And I meant it. But these two are small and round and rather friendly, so let them simply drift past you. 67 and 73. The baby picture clock. Planck and the standard model wound forward across 14 billion years. Predicts that the universe today should be expanding at about 67 in the units cosmologists use. The ladder clock, parallax and seepides and exploding stars, measured in the here and now, reads about 73. Let me take a slow moment with those units, because they sound worse than they are. The full phrase is kilometers per second per megaparsec. And here is the gentle translation. A megaparsec is a distance, about 3.25 million light years. A reasonable gap between galaxies. The number simply says, for every megaparsec of distance you look outward, the galaxies there are receding about 67 or 73 kilometers per second faster than the ones a megaparsec closer. Distance buys speed. That is the whole meaning. The farther, the faster. And the number gives it the exchange rate. Now, 67 and 73. Your first instinct, lying there comfortably, might be to think, well, those are pretty close, and your instinct is right. They differ by about 8%. If two bathroom scales disagreed about your weight by 8%, you would not question the laws of physics. You would buy a better scale. Here is why cosmologists cannot do that. And this is really the heart of tonight's mystery. So let it settle in slowly, like the room getting darker. Every serious measurement in science comes with an error bar, an honest admission of uncertainty. A measurement is not a point. It is a small range, a way of saying, the true value is almost certainly somewhere in here. And in the early days of this science, the error bars were enormous. For much of the 20th century, astronomers argued about whether the expansion rate was 50 or 100, a disagreement of a factor of 2. And the argument was famously bitter. Its two great champions, Alan Sandé, the heir to Hubble's own program, and Gérard de Vaucouleurs, a French-American rival of equal stubbornness, defended 50 and 100 respectively for decades. And colleagues from that era describe conference rooms that went quiet when both men were in them. In 1996, there was even a formal public debate in Washington about the number, with error bars that wide. A gap between 67 and 73 would have been invisible, two fuzzy clouds overlapping in a fog. But then the instruments improved. The Hubble Space Telescope flew, and one of its founding purposes was precisely this: to pin down the expansion rate. Gaia flew, Planck flew, decades of work, thousands of careers, and the error bars shrank and shrank. The baby picture prediction sharpened to better than 1%. The ladder measurement pushed its own claimed uncertainty down toward 1% as well. The two fuzzy clouds condensed into two sharp points, and the points did not move toward each other. That is the quiet turn at the center of this story. As error after error was hunted down, the gap between the clocks did not narrow. It stood still. 67 here, 73 there, each side publishing smaller and smaller error bars. The space between them turning from a blur into a wall. I will add the careful footnote, because it matters. Shrinking error bars measure the uncertainties a team knows how to count. There is always a further question, whether some subtle bias sits outside the count. And that question is exactly where the story is headed. But taken at face value, the numbers had stopped being fuzzy, and they had not stopped disagreeing. Scientists measure the seriousness of such a disagreement in units called sigma, and I will keep this as soft as the hour deserves. Sigma is a way of asking, what are the odds? This gap is just coincidence, just the random jitter of imperfect measurements. 1 sigma disagreements happen constantly. They are the weather of science. 3 sigma raises eyebrows. 5 sigma is the traditional threshold at which physicists stop saying fluke and start saying discovery. Roughly the confidence level at which the Higgs boson was announced in 2012. By 2022, when Riess and his colleagues published their most complete ladder measurement, built on more than 1,000 Cepheid stars observed by the Hubble Space Telescope, the tension for this specific comparison, their ladder against the Planck prediction, had crossed 5 sigma. Taken at face value, odds of about 1 in a million that chance alone could open a gap that size. I say for this specific comparison deliberately, because not every method lands so far from the prediction, and you will meet an important dissenting measurement soon. And picture, for a moment, what that number did to the field, because science is made of people, and the people were feeling it. In the summer of 2019, cosmologists from around the world gathered at the Kavli Institute for Theoretical Physics, in a building overlooking the Pacific in Santa Barbara, for a meeting devoted entirely to this tension. Attendees describe an atmosphere unusual for a physics conference. Standing room in the seminars. Arguments continuing over dinner. A sense that something in the foundations was creaking. We will return to something said at that meeting later tonight, because it belongs in a chapter of its own. For years, the respectable position remained that some subtle, systematic flaw would eventually surface, most likely in the ladder, since the ladder has more rungs to worry about. Maybe the Cepheids in distant galaxies were blended with neighboring stars in Hubble's slightly blurry images, making them look brighter than they truly were. Maybe dust was playing tricks. Maybe the calibration at the bottom was off by a hair, and the hair had climbed the ladder and grown into the whole gap. These were not lazy objections. They were the responsible ones. The questions Riess's own team asked themselves relentlessly, because the alternative was expensive beyond imagining. The alternative was that the standard model of cosmology, the equations that wind the baby picture forward, the framework that has passed test after test for a quarter of a century, is missing an ingredient. An 8% crack does not sound like much, but an 8% crack in the foundation of a house is not 8% of a problem. It is a different kind of problem entirely. So the field needed two things. It needed to understand the man defending 73, what he had seen before, and why his colleagues took him seriously, even while doubting him. And it needed an instrument sharp enough to test the favorite suspicion directly. The man comes first, because decades earlier, as a young researcher barely out of graduate school, Adam Riess had already once found an impossible number in his data, checked it until his hands ached, and watched it turn out to be true. That story has a Nobel Prize at the end of it. It begins with a question about how the universe will die. Every long mystery has a moment when it stops being about instruments and becomes about a person. So let me introduce you properly to the astronomer whose ladder now hangs at the center of our story. Because the most important thing about Adam Riess is not his Nobel Prize. It is that he has stood in this exact spot before, holding a measurement that the world assumed was a mistake. Picture the mid-1990s. Riess is in his 20s, a graduate student at Harvard, working under an astronomer named Robert Kirshner, and his specialty is almost comically narrow. He studies the light curves of exploding stars the precise way a Type 1, a supernova, brightens and fades over the weeks of its death. You remember those explosions from our ladder, the standardized flashbulbs. Riess's early claim to fame was a statistical method for reading their light curves more honestly, squeezing cleaner distances out of them by correcting for dust and for each explosion's individual quirks. Careful, unglamorous work, rung polishing, the family trade of nearly everyone in this story. After Harvard, he moved to Berkeley, in California, and joined a small international team with a bluntly descriptive name, the High Z Supernova Search Team. Organized by the astronomer Brian Schmidt in Australia, their plan was simple to state and brutal to execute. Find Type 1, a supernovae in galaxies billions of light years away. Measure their distances and compare those distances to the stretch in their light. Do that for enough explosions, and you can measure how the expansion of the universe has changed over cosmic time. And nearly everyone in the field expected the same answer. The expansion had to be slowing down. The universe is full of matter. Matter pulls on matter, and gravity is the great brake. The question worth a career was how hard the brake was pressing. Measure the deceleration, and you would learn the fate of the cosmos, whether it would expand forever, coasting into the cold, or someday slow, stop, and fall back in on itself. There was even a rival team racing them, a group at Lawrence Berkeley National Laboratory called the Supernova Cosmology Project, led by a physicist named Saul Perlmutter. Two teams, one number, and a certain amount of entirely human rivalry. Through 1997 and into 1998, Riess sat down with the team's hard-won data, dozens of distant explosions, and began extracting that number, the deceleration of the universe, and the number came out negative. I want you to sit with that the way he had to. a negative deceleration, not a slowing, a speeding up. The data were saying that the expansion of the universe is accelerating, that the galaxies are not coasting apart against gravity's pull, but are being pushed faster and faster by something which, according to everything then understood, was roughly like dropping your keys and watching them fall upward, gaining speed as they went. Riess has described, in interviews over the years, going back through the analysis, assuming he had made an error, checking the software, checking the dust corrections, checking everything. A careful person checks when the answer cannot be right. The answer stayed. He shared it with the team, and the team reacted the way honest scientists react, which is to say, with distress. Brian Schmidt has often described his own reaction as somewhere between amazement and horror, because everyone on that team understood the first rule of extraordinary claims. The most likely explanation was that they were wrong, and wrong publicly, at the start of their careers. And here is the detail that turns this from anecdote into a lesson. The reason this chapter matters for everything still ahead of us tonight. Across the bay, the rival team was finding the same impossible thing, independently, with their own supernovae, their own software, their own corrections, their own biases. In early 1998, the two competing teams, who shared little except mutual suspicion, announced results that agreed. The expansion of the universe is speeding up. Science does not have many higher forms of confirmation than that. Two groups who would have loved to catch each other in an error, arriving at the same forbidden conclusion. Now, precision matters here, and this is a place where I owe you a careful sentence. What the two teams discovered was the acceleration. That is the measured fact, confirmed many times since. The push behind the acceleration needed a name, and the physicist Michael Turner soon coined one: dark energy. But the name is a label for a mystery, not a solved ingredient. To this day, nobody knows what dark energy is. In the Standard Model's bookkeeping, it accounts for roughly 68% of the energy content of the universe, and the model handles it in the simplest way mathematics allows, as a cosmological constant, an unchanging property of space itself, the same yesterday, today, and forever. Whether that simple assumption is true will matter a great deal later tonight. So tuck it somewhere soft. 13 years after the discovery, in 2011, the Nobel Prize in Physics went to Saul Perlmutter, Brian Schmidt, and Adam Riess. The impossible measurement had become a foundation of modern cosmology. The keys really do fall upward. Why does this story belong in a night about two disagreeing clocks? Because of what the experience teaches and what it does not. You might assume that being right against the world breeds arrogance, a habit of trusting your own numbers over everyone's doubts. People who know the field will tell you it tends to do the opposite. The discovery of 1998 survived because it was checked into the ground, because a rival team existed, because every mundane error was hunted before anyone dared believe the exciting conclusion. The lesson was never, trust yourself. The lesson was, the universe is under no obligation to match your expectations. And the only way to know anything is to check until your hands ache. So when, years later, this same man began measuring the present-day expansion rate, and his number kept coming out above the baby picture's prediction, he did not race to announce a broken model. He assumed, like nearly everyone that something in his own ladder was loose. And he organized one of the longest campaigns of self-doubt in modern astronomy to find it. That campaign is the next chapter of our night. It has no explosions in it, and no prizes. It has something quieter. A scientist spending year after year trying to destroy his own result. And failing. Let your breathing slow. The young man with the impossible number is about to spend 20 years asking whether he fooled himself. There is a version of science that lives in movies. All blackboards and eureka moments. And then there is the version that fills the actual years, which looks like this chapter. Checking, rechecking, building a better ruler, measuring the same thing again, and frowning at the same answer. If that sounds monotonous, I promise it is the good kind of monotonous, the kind you are allowed to drift off inside, because what follows is really one long story of a man and a field, trying to catch a mistake that kept refusing to be caught. A word on the title of this stretch of our night. By the way, the modern, sharp-edged version of the Hubble tension took shape through the 2010s. But the doubting began earlier, in the middle 2000s, when the campaign you are about to hear was born. Added up, and 2 decades is about right. Begin in 2005, or thereabouts. The discovery of acceleration is 7 years old. The Nobel Prize is still 6 years away. And Riess, now at Johns Hopkins and the Space Telescope Science Institute in Baltimore, starts a new project with a name only astronomers could love. SHOES. It stands for supernovae and H0 for the equation of state. And never mind the mouthful. The mission is simple. Rebuild the cosmic distance ladder, rung by rung, with modern instruments, and measure the present-day expansion rate, the number called H0, to a precision nobody had achieved. When the project begins, that number is known to within roughly 10%. The dream is 1%. Picture the early years of that campaign, because they had a rhythm to them. Proposals written and rejected and rewritten, because time on the Hubble Space Telescope is among the most fought-over resources in science. Then, when time is granted, the long nights of scheduling, the images arriving as data files in the small hours, a graduate student somewhere in Baltimore opening them first, running the photometry, watching a Cepheid's heartbeat emerge from the numbers as a clean curve on a screen. There is a particular kind of joy in that moment. Quiet and private. A star 400 quintillion miles away, keeping time like a metronome in your laptop. Multiply that moment by hundreds of stars, then by years, and you have the texture of the work. Year after year, the ladder tightened. The team anchored the candles to geometry, to Gaia's parallaxes, and to a special galaxy called NGC 4258, where a disk of water molecules orbiting a black hole acts as a natural radio beacon, giving a distance almost as direct as triangles. Rung by rung, the claimed uncertainty fell. 10%, 5, 3, and the answer kept coming out near 73. Meanwhile, as you remember, the baby picture's prediction was sharpening towards 67 through the 2010s. The gap hardened from a curiosity into a confrontation, and so began the great error hunt. Rather than walk you through it as a list, Let me give you its flavor through the questions. Because each question consumed years of someone's life. Could unseen neighbor stars be contaminating the candles? Cepheids in distant galaxies are faint, and Hubble sees them slightly blurred. So the light of crowded neighbors can blend in, making a candle look brighter than it is, which shortens the inferred distance, which pushes the expansion rate up. This suspicion, called crowding, became the favorite. The team attacked it with artificial star tests, injecting fake stars into real images to measure the bias directly. The answer held, but critics could still say, "You are correcting a blur with a model of a blur," and the doubt survived. Patient of dust. Speaking of dust, could it be dust? Interstellar dust dims and reddens starlight. Decades of work went into correcting for it, using the colors of the stars themselves. The answer held. Could the candles themselves vary with chemistry? Stars in different galaxies are built from gas seasoned with different amounts of heavy elements, which might subtly shift a Cepheid's brightness. Measured, modeled, corrected. The answer held. Could the anchor be off? For years, the ladder leaned on the large Magellanic Cloud, the very cloud Leavitt had studied. Then astronomers measured its distance to about 1% using eclipsing pairs of stars. And Gaia delivered geometric parallaxes for Cepheids in our own galaxy by the dozens. The anchor was rebuilt in triplicate. The answer held. And here I owe you the most important complication in this chapter. Because honest science has more than one voice, and this voice belongs in our story permanently. Her name is Wendy Freedman. She is an astronomer at the University of Chicago, and she is not a critic sniping from the sidelines. She led the landmark Hubble Space Telescope program that, in 2001, delivered the first truly modern measurement of the expansion rate, 72, with 10% uncertainty, the result that ended the era of 50 versus 100. She has spent her career on exactly these rungs, and through the 2010s, as the tension sharpened, Freedman urged caution, arguing that the Cepheid rungs carried subtleties not fully tamed, and she built an alternative second rung from a different kind of star entirely, the brightest red giants, whose peak brightness can serve as a standard candle and which live in the calm outskirts of galaxies, far from the crowded neighborhoods where Cepheids blink. Some of her team's analyses returned values near 70, in the uncomfortable middle ground between the clocks, to some scientists, that hinted the tension might yet dissolve into stellar physics. To others, the red giant method carried its own subtleties. The disagreement between these two careful camps was real. It was argued in respectful and occasionally pointed papers, and parts of it remain unsettled tonight. Hold Freedman's voice in your mind, because a field that contains her is a field still doing its job. By 2022, Shoes published the measurement 17 years of work had been building toward more than 1,000 Cepheids, dozens of galaxies, 4 independent anchors, a claimed uncertainty of about 1%, 73, plus or minus 1, against the baby picture's 67.4, plus or minus half. For this comparison, 5 sigma, the wall in the hallway, fully built, and yet one suspect still stood, the favorite, crowding, wearing its shadow of doubt that no statistical argument could fully dispel. because every distant Cepheid on the ladder had been photographed by Hubble, and Hubble's blur at those faint limits was simply a fact of its mirror. What the field needed was not another model of the blur. It needed vision without the blur. It needed to look at the same stars in the same galaxies and see them cleanly separated from their neighbors. So the question, were the candles lying, could be answered by looking instead of arguing. By then, such vision existed. It had unfolded, mirror by golden mirror, 1,000,000 miles from home, built for 100 purposes, and available, as it happened. For this one long phase of checking was about to receive a much sharper test. The telescope that would deliver it is a story in itself. A story of foil thinner than a hair and mirrors adjusted by the width of atoms. And it deserves a chapter told slowly, which is exactly what comes next. The hunt has lasted 20 years. The hunters are patient. So is the answer. Everything we have followed tonight, the candles, the ladder, the baby picture, the 20 years of doubt, now funnels toward a single machine. So let us take our time with it, because there may be no more soothing image in modern science than this one. A telescope the size of a tennis court, gliding through silence, 1,000,000 miles from home, staring into the dark with eyes cooled nearly to the temperature of the dark itself. The James Webb Space Telescope took roughly 3 decades to imagine, design, and build, the work of thousands of engineers and scientists on multiple continents, many of whom spent whole careers on a single component. A hinge, a coating, a cable that had to unspool in zero gravity exactly once and exactly right. And I want to be clear, one more time, about what it was for. Webb was never a single-purpose machine, and it certainly was not built to settle the argument between our two clocks. It is a general observatory, designed to study the first galaxies, the nurseries of stars, the atmospheres of distant planets, 100 things at once. But its particular kind of vision happened to be exactly what our mystery required. And to see why, you only need one idea. And it is a gentle one. Webb sees infrared light, the kind of light that warm things give off. Your eyes see the narrow band of colors from violet to red. The Hubble Space Telescope sees mostly that same band. Webb was built for the longer waves beyond red, the glow that a cooling cup of coffee gives off in a dark kitchen, invisible to your eye, but real and measurable, and everywhere in the universe. Infrared matters to our story for 2 reasons. The first is dust. You remember dust, one of the suspects. The fog that dims and reddens starlight and complicates every candle. Dust grains are small, and they are good at blocking short wavelengths. But longer infrared waves flow around them, the way ocean swells roll past a pier post while ripples are stopped by it. Point an infrared eye at a dusty galaxy, and the fog thins dramatically. The second reason is sharpness where it counts. At the infrared wavelengths where Cepheids had been measured, Webb's enormous mirror delivers far crisper images than Hubble could manage. And crispness is precisely what the crowding question had been begging for. Stars that blur together in Hubble's view stand apart in Webb's, but an eye that sees the light of warmth has a problem. And the problem is itself. A warm telescope glows in exactly the light it is trying to detect. Pointing a warm infrared telescope at the sky is like trying to stargaze with a flashlight taped to your forehead. So Webb had to be made cold, and kept cold, using nothing but shade. That is the purpose of the sun shield, and I find it one of the most restful facts in engineering. Webb carries 5 layers of a silvery foil-like material, each layer thinner than a human hair, stretched taut, one above another, with vacuum in between. Sunlight strikes the first layer, and most of its heat is turned away. What leaks through radiates sideways into space before reaching the next layer. And again, 5 times. On the sunny side, the shield bakes at roughly 200 degrees Fahrenheit. On the shaded side, a few feet away, the telescope rests around -370, cold enough for its mirrors to fall silent in the infrared and see nothing but the universe. And those mirrors, 18 hexagonal segments of beryllium, each coated in a whisper of gold, a layer so thin that all of it together weighs about as much as a golf ball. Gold, because gold is superb at reflecting infrared light. The segments fold to fit inside a rocket and open in space into a single mirror over 21 feet across, with roughly 6 times the collecting area of Hubble's. Each segment rides on tiny motors that can adjust its position by a fraction of the width of an atom, so that 18 mirrors become, optically, one eye. There was a catch, and for years it kept astronomers awake, in a way I hope tonight does not keep you. Hubble orbits close to Earth, and when Hubble broke, astronauts flew up and fixed it 5 times. Webb could not live near Earth, because our planet is warm, and warmth is blindness for an infrared eye. So Webb was sent to a special place called the second Lagrange point, a pocket of gravitational balance about 1 million miles away, 4 times farther than the Moon, where the Sun and Earth stay on the same side. So one shield can shade it from both. No astronaut has ever traveled a quarter of that distance. If anything failed to unfold, there would be no repair. The mission counted its single points of failure, the steps where one stuck bolt would end everything. In the hundreds. Webb launched on Christmas morning, 2021, from a spaceport in French Guiana, folded like a moth in the nose of a European rocket. Over its first 2 weeks, it performed the transformation everyone feared. The shield unspooling layer by layer, the mirror wings swinging into place, hundreds of release mechanisms firing in sequence. Then, over the following months, it cooled, aligned its segments atom width by atom width, and calibrated its instruments. Astronomers around the world followed each step the way families follow a surgery. Every deployment worked. In July of 2022, the first images were released, and even people who had spent their lives on the machine described being unprepared for their sharpness. The observatory then set about its 100 purposes: deep fields and infant galaxies, and the weather on far-off worlds. But among the proposals approved in its early cycles were several aimed much closer to home, at a handful of unremarkable-looking spiral galaxies within a couple 100 million light-years. Galaxies that happened to hold rungs of a certain ladder. The sharpest eyes ever opened were about to look for the loose bolt. What follows is what they found, and just as important, what they did not. Think back, one last time, to the shadow that 20 years of checking had never fully dispelled. Crowding. Every Cepheid on the far rungs of the ladder had been measured by Hubble, and in Hubble's slightly soft images, a candle's light could blend with the light of unseen neighbors, making it look brighter than it truly was, tilting every distance, inflating the final number. The corrections for this were careful and statistical, and, in the eyes of skeptics, forever uncertain. You can model a blur, you cannot be certain of a blur. The only cure was to remove it. So beginning in Webb's first year of science, the show's team pointed the new telescope at galaxies along the ladder, the same galaxies, the same Cepheids that Hubble had measured, and photographed Leavitt as candles again. The comparison images were published openly, and they say everything. In the Hubble image, a Cepheid sits in a granular haze, its light shouldering into the light of its neighbors. In the Webb image of the same patch of sky, the haze resolves into individual stars, sharp and separate, and the Cepheid stands alone, clean, measurable. Here is what a loose bolt would have looked like. If crowding had been fooling the measurements, the clean Webb photometry would come out systematically fainter than Hubble's, and the effect would grow with distance. Since farther galaxies are more crowded in the frame, the distances would stretch. The ladder's answer would sink from 73 towards 67, and the tension would begin to dissolve. That is not what the images showed. Star by star, galaxy by galaxy, Webb's measurements landed on top of Hubble's. The rhythms matched, the brightnesses matched, with no drift as the team looked farther out. The first results, published in 2023, covered a few ladder galaxies and confirmed Hubble's photometry there. Skeptics reasonably noted that a few galaxies are not a ladder, so the campaign widened. And, by late 2024, the team had reobserved the hosts of roughly a third of the ladder's supernova calibrators, more than 1,000 Cepheids, reaching out to the most distant galaxy where Hubble had measured them well. Across that whole span, the two telescopes agreed to within about 1%. In the team's published analysis, the specific suspicion that had shadowed the ladder for a decade, unrecognized crowding in Hubble's Cepheid photometry, biasing the result with distance, was ruled out as the source of the tension at very high statistical confidence, around 8 sigma in their accounting. Now, I made you a promise in the first minutes of tonight, and this is one of the places it matters most. So let me draw the boundary of this result as carefully as the team itself did. What Webb established is that Hubble's Cepheid measurements were sound, the favorite suspect. The error nearly everyone expected to find is not there. What Webb did not establish is that no error of any kind remains anywhere. The reobserved sample, large as it is, still covers a fraction of the full ladder. The alternative rungs, built from other stars, still disagree among themselves about the final digit, and Webb tested the ladder clock, not the baby picture clock, whose own analysis rests on its own long chain of care, ruling out one explanation, even the leading one, is not the same as proving the exciting alternative. The honest summary is this: the tension was given one of the hardest observational tests anyone knew how to give it. A test with the power to kill it, and it survived. And here, our dissenting voice returns, because the story is better and truer with her in it. Wendy Freedman's team also turned Webb toward the ladder, building distances 3 ways at once. from Cepheids, from the brightest red giants, and from a class of carbon stars. In her team's analysis, some methods leaned toward the lower, more comfortable number, and Freedman argued that the spread among the methods pointed to systematic errors not yet tamed, not to new physics. In one much-discussed episode, reported in the science press in 2024, her team's preliminary numbers seemed briefly to ease the tension, until further checks, including a correction her own group found and fixed in its Cepheid analysis, moved the result back up toward Riess's. The two camps continue to compare samples and swap criticisms in the journals, which is, whatever the headlines say, exactly what a functioning science looks like. Their remaining disagreements are now about the final rungs and the final digits. On the question Webb was uniquely able to answer, whether Hubble's candle photometry had been lying, their instruments saw the same thing. It had not. So the field arrived at the situation it had spent 2 decades trying to avoid. And I will state it in the careful form it deserves. The ladder's most doubted link has been checked with sharper eyes and has held. The prediction from the infant universe has not moved. The gap between 73 and 67 remains. Harder now to blame on the favorite mistake, not yet proven to be anyone's discovery. The results did not prove new physics. They allowed the possibility of new physics to survive its strongest test so far. There is a particular feeling in science when the most likely mundane explanation dies. And it is not despair. People who lived through such moments describe something closer to a held breath. The quiet in a house just after a knock at the door. If the instruments are right, and the checking holds, then the discrepancy may be trying to tell us something. And the man who had spent his life expecting to find his own mistake now had to weigh a stranger thought. What he actually said, on the record, with sources you can trace, is where we go next. The candles have kept their side of the story. Now the people speak. I promised you in the first minutes of tonight that when we reach the words themselves, the statements of the actual scientists, I would give them to you from the record, with their sources named in the telling, so that nothing rests on rumor or on a headline. This is that chapter. Begin with the man himself. In March of 2024, when the large Webb and Hubble comparison was published in the Astrophysical journal Letters, the European Space Agency and NASA carried Adam Riess's summary of the result in their official science releases. He said the team had now spanned the whole range of what Hubble observed and could rule out a measurement error as the cause of the tension with very high confidence. And then he added the sentence that travelled around the world. With measurement errors negated, he said, what remains is the real and exciting possibility that we have misunderstood the universe. Let that settle for a moment, because every word is doing work. He did not say, we have misunderstood the universe. He said, the possibility remains. And he called it real. And he called it exciting. And, notice the boundary inside his own phrasing. The errors negated were the specific ones his team had tested. The measurement errors in the candle photometry. This is how a careful scientist speaks at the edge of the known. And it is still an extraordinary sentence for such a man to put his name to. The person who spent 20 years hunting his own mistakes, telling the world, through an official space agency release, that the flaw may live in our picture of the cosmos instead. Later that same year, in December of 2024, his team published a larger Webb analysis in the Astrophysical journal, and in the statement accompanying it, Riess said, "The discrepancy between the observed expansion rate and the Standard Model's prediction suggests our understanding of the universe may be incomplete." With two flagship telescopes now confirming each other's findings, he said, "The problem must be taken very seriously." And he called it a challenge, but also an incredible opportunity to learn more about our universe. And when a science journalist at the news site Live Science asked him about the widening investigation, he put it more plainly still, saying that the more work his team does, the more apparent it becomes that the cause is something much more interesting than a telescope flaw. Interesting, exciting, opportunity, notice, drowsily, without effort. That these are not the words of a man announcing a catastrophe. They are the words of a man who has seen the universe surprise him once before and recognizes the feeling of standing at the start of something rather than the end. And to be fair to the whole field, these are Riess's readings of his own team's results, stated in his team's releases. They are not a proclamation issued on behalf of all cosmology. You already know that Wendy Freedman, with the same telescope, reads the situation more cautiously. Both readings are part of the record. But Riess is not the only Nobel laureate in this story. And here is where the warning in our title truly comes from. Remember the gathering I mentioned in the summer of 2019 at the Kavli Institute for Theoretical Physics in Santa Barbara, a conference devoted entirely to the tension. The Institute's director at the time was David Gross, who shared the Nobel Prize in Physics in 2004 for work on the force that binds atomic nuclei. Science journalists covering the meeting reported his assessment of the situation to the assembled cosmologists. In physics, he explained, this would not be called a tension or a problem. The proper word, he said, was crisis. A crisis, in the mouth of a Nobel laureate, speaking about the foundations of cosmology, with reporters in the room. That is the sentence behind many of the dramatic headlines you may have seen, and now you know its shape exactly. He was not saying the sky is falling. Physicists of his generation use that word with something almost like appetite, because in the history of their field, crisis is where the treasure is buried. The crisis over the glow of hot objects gave us quantum mechanics. The crisis over a misbehaving planetary orbit gave us general relativity. When Gross says crisis, part of what he means is, pay attention. This is the interesting kind. And what of the exact phrase in our title tonight? A different universe. Here I owe you the cleanest honesty of all. I cannot hand you a paper or a transcript where those 4 words sit in quotation marks beside a laureate's name, and so I will not pretend they do. That phrase is how headlines and popular retellings have compressed the situation. What stands on the record is what you have now heard with your own ears. A Nobel Prize winner stating, through NASA and the European Space Agency, that we face the real and exciting possibility of having misunderstood the universe. Another Nobel Prize winner, at a scientific conference, choosing the word crisis. That is the sense in which the phrase a different universe is used in the title of tonight's story, not as a quotation, but as a plain language description of a model that may be incomplete, offered by the people who know that model best. One more voice belongs here, for balance. And you know her by now. When Freedman's Webb results were reported, she told the science magazine Quanta that the disagreements among the stellar methods were not telling us about fundamental physics. They were telling us that some systematic error remains in one or more of the distance methods. And she added a sentence I find quietly beautiful. A promise of her own. With the improvement in the data, she said, this is going to be solved. And she expected the field to get to the bottom of it. So here is where the record stands. As you drift there in the dark, one laureate says, we may have misunderstood the universe, and calls the prospect exciting. Another calls the situation a crisis, and half means it as a compliment. A third master builder says, check the rulers once more, and promises the answer is coming either way. Nobody is guessing in secret. Nobody is hiding the disagreement. The argument is published, sourced, and ongoing, and you have now heard it more accurately than almost anyone who only read the headlines. While all of this was being said, the same golden telescope was gathering other strange news from the deepest reaches of the early universe. And, from a mountaintop in Arizona, a very different instrument was mapping millions of galaxies with a puzzle of its own. Those findings are often stacked into the same headlines as our two clocks, and the next chapter will take them slowly and carefully and on their own terms. The words are on the record. Let them keep the watch for a while. Before this chapter takes a single step, I want to set down its ground rule, because everything that follows depends on it. You are about to hear of two more puzzles from the frontier of cosmology, and they will sound, at first, like siblings of the one we have followed all night. They may not be. These findings may be entirely unrelated to the two clocks and to each other. Placing them in the same chapter does not mean they share a cause. And no one has shown that a single new theory would explain them all. A hallway can have 3 odd noises in it for 3 boring, separate reasons. I tell you this now because headlines often stack these stories into one grand crisis. And the truth is both calmer and more interesting. What they genuinely have in common is only this. Each is a place where new instruments are asking old assumptions to prove themselves again. With that said, let us visit them. Slowly. The first puzzle arrived almost as soon as Webb opened its eyes. In its first deep images, in 2022, astronomers searching for the earliest galaxies found them. Which was the plan? What was not the plan was how they looked. Some of the candidates, seen as they were only a few 100 million years after the Big Bang, appeared startlingly bright, and early analyses suggested some might be startlingly massive, as if they had grown billions of suns worth of stars in a cosmic instant. Headlines declared that Webb had found impossible galaxies, and a few claimed the Big Bang itself was in trouble. Here is the calmer truth. Told at bedtime pace, some of those early estimates softened. Exactly as careful scientists warned they might. Judging a young galaxy's mass from a few points of light involves assumptions about its stars. And when proper spectra were taken, some candidates proved closer than they first appeared, or lit by unusual conditions rather than impossible bulk. But not all of the strangeness went away, even after corrections. Many published analyses find the early universe building bright galaxies faster and earlier than the standard picture of galaxy formation comfortably expected. Webb also revealed a population of tiny, mysterious objects nicknamed little red dots, whose nature is still openly argued. Possibly compact galaxies. Possibly young black holes wearing shrouds of gas. Possibly something else. And I want to be plain about the size of this puzzle. Nothing here overturns the Big Bang, which rests on the baby picture and much else. What is being strained is a softer, higher layer of the model. Our understanding of how quickly the first structures assembled and lit up, that is a genuine open question about cosmic childhood, whether it connects at all to the disagreement between our two clocks. Nobody has demonstrated. It may simply be a separate lesson, that infant galaxies were in more of a hurry than our simulations guessed. The second puzzle is newer and potentially deeper, and it comes not from Webb, but from a ground-based instrument on a mountaintop in Arizona called DESI, the Dark Energy Spectroscopic Instrument. DESI is a marvel of patience. A telescope fitted with 5,000 small robotic positioners that can capture the light of tens of millions of galaxies, building the largest three-dimensional map of the universe ever made. Buried in that map is a fossil, a preferred spacing between galaxies, left over from the same sound waves that rippled through the infant cosmos and printed the baby picture. That fossil ruler lets DESI trace how expansion has changed across billions of years. Era be era, like growth rings in a tree. In 2024, and more strongly in its 2025 data release, the DESI collaboration reported something that made the field sit up straight. Taken alone, I should say clearly, DESI's map remains consistent with the standard model. But when the map is combined with the baby picture and with the supernova records, the combined data show a statistical preference for a dark energy that is not constant. A dark energy that may have weakened over cosmic time. The strength of that preference has ranged from roughly 2.8 to about 4.2 sigma, depending on which datasets are combined. You remember our gentle rule. That is eyebrow-raising territory, genuinely suggestive, and short of the 5 sigma line where physicists declare discovery. It could still fade, as such hints sometimes do, and the DESI scientists say so themselves in their own papers. But feel what is at stake. Without gripping it, the standard model's simplest assumption, the one Riess's own discovery wrote into the books, is that dark energy is a cosmological constant, unchanging, the same yesterday and forever. That assumption is woven into the second clock, into the winding forward of the baby picture across 14 billion years. If dark energy turns out to evolve, the model that predicts 67 was predicting with a slightly wrong ingredient list. Would that reconcile our two clocks? Here is the humbling part, and it deserves honest emphasis. Not obviously. Some proposed revisions ease the tension. Others, awkwardly, make it worse. The relationship between the DESI hints and the Hubble tension is an open research question, actively contested, and anyone who tells you tonight that one solves the other is ahead of the evidence. So let me say carefully what this chapter amounts to. Not a pattern, not one crisis with 3 faces. What has accumulated is a set of open questions, each with its own evidence, its own suspects, and its own chance of dissolving into better data. The expansion rate question, tested and surviving. The early galaxy question, real but possibly parochial. The dark energy question, tantalizing and unconfirmed. Together, they have encouraged some cosmologists to ask whether several parts of the standard picture deserve renewed testing, while others caution, with equal expertise, that these are likely separate problems with separate answers. Both camps agree on one thing only, that the coming years of data will speak. And in the meantime, theorists have not been idle. For the oldest and sharpest of these questions, the two clocks, they have assembled a whole gallery of candidate explanations, ranging from the elegant to the wonderfully strange. Walking that gallery is the next stretch of our night, and it asks nothing of you but curiosity. 3 odd noises in the hallway, maybe 3 causes, maybe fewer. The house keeps its counsel, and the night is patient. Every good mystery reaches the chapter where the detective lines up the suspects, and ours has arrived. So picture, if you like, a long, quiet gallery, the kind you might wander on a rainy afternoon, and in it a row of portraits, each one a candidate explanation for why the two clocks disagree. We will stroll past them slowly. None has been convicted. Several may be innocent. It is entirely possible the guilty party is not on display at all, because nobody has painted its portrait yet. Tonight, we are not here to solve the case. We are here to enjoy the gallery, and as we walk, I will do something the plaques in real galleries do, and tell you how each idea is regarded, which ones are widely studied, which are speculative, which are minority views, because hanging them side by side should not suggest they hang with equal weight. One piece of orientation first, because it explains many of the portraits. Remember how the second clock works. It takes the baby picture, applies the standard model, and winds forward to predict today's expansion. That prediction leans on a kind of cosmic yardstick. The distance sound waves could travel in the young universe before the fog lifted. Many of the most discussed new physics proposals work by changing that early yardstick. If something made the infant universe expand a little faster than we think, the yardstick shrinks, and when cosmologists recalculate, the prediction rises from 67 towards 73, and the clocks chime together. Not every suspect works this way. Some aim at later eras, at our own neighborhood, or at gravity itself. But the early yardstick is where the most crowded wing of the gallery hangs. Keep that one idea in your pocket, and the tour will feel easy. The first portrait, probably the most studied of the new physics ideas, is called early dark energy. You know, ordinary dark energy, the push dominating the cosmos today. This proposal, developed by theorists including Mark Kamiankowski of Johns Hopkins, the same university where Riess builds his ladder, imagines a separate, brief episode of dark energy in the universe's first tens of thousands of years. A short extra push, accelerating the early expansion just enough to shrink the yardstick, then fading rapidly, but not, and this matters, fading without a trace. An episode like that would leave subtle fingerprints in the baby picture's fine ripples and in how galaxies later clustered. And those fingerprints are exactly how the idea is being tested. So far, the verdict is genuinely mixed. Some analyses find room for it. Others find the fit strained, and the model must thread an increasingly narrow needle. Widely studied, actively tested, unconfirmed. The second portrait is a family group, the exotic relatives of the neutrino. Neutrinos are real. ghostly particles that flood the universe, passing through your body right now without a whisper. And their behavior in the early cosmos genuinely shapes the yardstick. Some theorists propose additional neutrino-like particles, or new interactions among them, subtle enough to hide from laboratories so far, present enough in the first instance to nudge the early expansion, respectable, testable in principle, and steadily squeezed. As experiments and the baby picture keep narrowing where such ghosts could hide, widely studied, increasingly constrained. The third portrait has a certain mischief in it. Primordial magnetic fields. If faint magnetic fields threaded the universe before the fog lifted, they could have stirred the plasma into small clumps, changing when atoms formed, and shortening the yardstick. The physics is not exotic. It is the physics of refrigerator doors relocated to the dawn of time. Whether such fields existed at the right strength is unknown, speculative but published, and taken seriously as a possibility worth checking. The fourth portrait proposes that one of nature's constants was not constant, a slightly different electron mass in the early universe, retuning the moment the fog lifted. Most physicists regard this as a heavy price, because the constants have been checked for drift with exquisite care and never caught. It hangs in the gallery because the arithmetic works better than you might expect. And because honesty requires the gallery to be complete, speculative, and viewed with heavy skepticism, the fifth portrait turns the suspicion around and asks, what if the problem is our neighborhood? Suppose our galaxy sits inside an unusually empty region, a vast local void. Matter around a void pulls outward. Nearby galaxies would recede a little faster than the cosmic average, and our local clock would read high, through no fault of its own, appealingly modest. No new particles required. Its trouble is that galaxy surveys do not clearly show a void deep enough, and the supernova ladder reaches far beyond any plausible neighborhood effect. Most analyses conclude it cannot carry the whole gap. A cousin of this idea, called timescape, goes further and questions whether describing a lumpy universe with one smooth expansion rate is valid at all. It has serious defenders, serious critics, and remains a minority interpretation under active debate. And the sixth portrait, painted mostly in shadow, is modified gravity, the possibility that Einstein's theory itself needs adjustment across cosmic scales. The most radical suspect and the most tightly constrained, because general relativity has passed every test from falling apples to colliding black holes. It hangs here because it has happened before that a theory passed every test until the one it failed. Tightly constrained, never quite dismissed. Now let me tell you what keeps the detectives humble, and it is a fine thought to drift on. Every suspect that eases the clock tension gets interrogated against all the other evidence. The baby picture's fine ripples, the galaxy maps, the supernova records, the ages of the oldest stars. And so far, everyone either fails somewhere or survives only in a weakened form that does not fully close the gap. Theorists have license to get creative. As Kamionkowski put it in a statement accompanying the 2024 results, and they have used it generously. Dozens upon dozens of published proposals. The universe, so far, has said no comment to all of them. That silence is not failure. It may simply mean the data are not yet sharp enough to convict anyone. It may mean the answer is a mundane systematic error after all, hiding in some rung nobody has thought to shake. Or it may mean the true portrait is still unpainted. History has seen all three endings, and it is worth knowing, before this night carries you off, what each one looks like from the inside, because there have been small stubborn numbers before. Two of them changed everything. Their stories are next. And they are the most comforting stories science knows how to tell. The gallery dims behind us. The rain, somewhere outside, has stopped. There is a particular fear that lives just under the headlines about all of this. And you may have felt its small cold draft at some point tonight. If the model of the universe is wrong, what else is wrong? Was everything we learned a mistake? The best answer to that worry is not an argument. It is a memory, because science has strained its finest models before. And what happened next is worth knowing in full, both the famous endings and the forgotten ones. So let me tell you two bedtime stories from the archives of physics. And then, because I promised you honesty over drama, a third kind of story that the first two usually crowd out. The first story is about a planet that would not behave in the 1800s. Newton's theory of gravity was the most successful idea our species had produced. For 2 centuries it had explained the tides, the moon, the wandering of every planet. It had even performed a magnificent trick. When Uranus drifted off its predicted course, astronomers trusted Newton so completely that they used the discrepancy to calculate the position of an unseen planet pulling on it. In 1846, a telescope in Berlin turned to the predicted spot and found Neptune, within about 1 degree of where the mathematics said it must be, a planet discovered not by searching, but by arithmetic. And yet, through that same century, one small number refused to cooperate. Mercury, closest to the Sun, traces an oval orbit that itself slowly rotates, like a flower petal pattern drawn by a spirograph. Newton's gravity, with every known planet's tug included, predicted that rotation almost perfectly. Almost. A tiny residue remained, an unexplained drift of about 43 seconds of arc per century. A second of arc is roughly the width of a coin seen from a couple of miles away. Mercury was misbehaving by less than a hair's width at arm's length per 100 years. Astronomers did exactly what our cosmologists have been doing all night. They hunted the mundane explanation. Perhaps the sun bulged slightly. Perhaps dust tugged the orbit. Most famously, perhaps another unseen planet lurked inside Mercury's orbit. And they trusted this suspect so much, they named it in advance. Vulcan. And respectable observers spent decades claiming glimpses of it during eclipses. Every claim evaporated. The tiny number stayed, hanging on the wall of physics like a picture nobody could straighten. Then, in 1915, Albert Einstein completed general relativity, built not to fix Mercury, but to answer a deeper question about space and time. When he applied his equations to Mercury's orbit, the missing 43 seconds fell out of the mathematics. Exactly. With nothing added by hand. Einstein later described being so excited that he felt palpitations of the heart. The smallest number in astronomy had been the fingerprint of a new universe, sitting in plain sight for 70 years, waiting for the idea that could read it. The second story starts with something as humble as a glowing coal. In the late 1800s, physicists tried to use classical theory to predict the light pouring from any warm object. An oven, a star, a fireplace. The theory worked beautifully for the reddish, long wavelength part of the glow, and then, at short wavelengths, it did not merely drift off course, it exploded, predicting that every warm object should blast out infinite energy in ultraviolet light, that a cup of tea should be a death ray. Physicists called it the ultraviolet catastrophe, and the catastrophe was in the theory, not in nature, which kept glowing gently. In 1900, a conservative German physicist named Max Planck found a patch if energy could only be emitted in discrete little packets. Quanta. The equations calmed down and matched every measurement. Planck reportedly regarded his own idea as a desperate mathematical trick and spent years hoping someone would explain it away. Nobody ever did. The trick was the truth. Those packets unfolded into quantum mechanics, the physics of atoms and chemistry and sunlight, the physics that would eventually give us the transistor, and with it every computer. And, in a lineage you can trace almost directly, the very device reading you this story tonight. Now, the third kind of story, the one the anthologies skip, and the one that keeps scientists honest. Not every stubborn number is a treasure. In 2011, an experiment in Italy reported neutrinos apparently traveling faster than light, at 6 sigma, a result that would have shattered relativity. Months later, it traced to a loose fiber optic cable and a clock error. In the 1960s, a Soviet team announced a new form of water, polywater, that thickened and froze strangely, and laboratories worldwide confirmed it for years, until it turned out to be ordinary contamination. The history of physics contains many anomalies that dissolved when the measurements improved. Persistence under scrutiny is what makes an anomaly interesting. It is not a guarantee of revolution. Our 2 clocks have earned the first description. Nobody can yet promise them the second. So hold the stories up to the light of our own mystery and feel what history actually offers. Not a prophecy, but a pattern of possibilities. A model so successful it discovered planets by arithmetic can still have an edge. A domain where something deeper pokes through, announced by a small number that will not go away, and a 6 sigma sensation can still be a loose cable. The difference is only ever settled by more checking, which is precisely what the people in our story are doing, on mountaintops and in orbit, tonight. And notice the gentlest part, the part worth falling asleep on. When Einstein arrived, Newton was not fired. Newton still lands our spacecraft. The old truths kept working the morning after the revolution, because they had always been true in their domain, and the revolution merely drew the domain's borders. If the 2 clocks are ever explained by new physics, the same will hold. The baby picture will still be real. The expansion will still be real. Leavitt's candles will still blink their honest rhythms. Nothing already measured will unhappen. 43 seconds of arc. A gentle overshoot in an oven's glow. 8% between 67 and 73. Perhaps a loose cable somewhere after all. Perhaps a young theorist's palpitations. Decades from now, as the gap closes on its own. Exactly. With nothing added by hand. Either ending is a good story. Only one of them can be true. And no one on earth knows yet which. Morning will not need the answer. Neither do you. We have spent the night walking through cracks and open questions, and you have been a patient companion. So now, let the story turn around, the way a long walk turns for home, and let us take a slow inventory of everything this mystery does not touch. Because here is a secret the headlines rarely mention. Even if the standard model of cosmology were revised tomorrow morning, you would wake up in the same bed, under the same sky, held by the same faithful physics as always. Let me prove it to you, gently, item by item, like counting breaths. The sun does not care about the Hubble tension. Its warmth on your face is made by nuclear fusion in its core, physics tested in laboratories on Earth, understood in detail, and utterly indifferent to whether the deep cosmos expands at 67 or 73. The sun has risen on schedule for 4.5 billion years, and tomorrow morning it will do it again. Without consulting a single cosmologist, gravity, here, does not care. The gravity holding you to your mattress operates in what physicists call bound systems, things held firmly together, and in bound systems, local forces overwhelmingly dominate over anything cosmological. The expansion of the universe has no meaningful stretching effect on atoms, on bodies, on planets, on the solar system, or even on our entire galaxy, all of it gripped by gravity and electromagnetism vastly stronger than the gentle cosmic tide. The stretching of space is something that matters in the enormous empty reaches between galaxy clusters. Far from every shore, you live on the shore, you have always lived on the shore. The stars you know do not care. Every star you have ever seen with your own eyes belongs to our Milky Way, our own bound island. The stars do drift, each with its own slow motion, but so slowly by human measures that the Big Dipper will remain recognizably the Big Dipper for tens of thousands of years. Orion will rise this winter, essentially where your grandparents saw it rise. The mystery we have followed tonight lies billions of light years beyond the farthest star your eye can find. The wallpaper of your nights is safe. And the science that carries your daily life does not care. The physics that flies airplanes, the chemistry inside your medicine, the electromagnetism carrying this voice to your ears. All of it was tested at human scales, millions of times over, and none of it depends on the recipe of the early universe. When Einstein enclosed Newton, not a single bridge fell down. Bridges were never resting on the parts of Newton that bent. In the same way, nothing in your world rests on the parts of cosmology now being questioned. I want to go one layer deeper, because the inventory of what does not change includes things more precious than bridges. The baby picture remains real, measured by 3 generations of satellites, and it is not going anywhere. The expansion of the universe remains real, confirmed by a century of redshifts. The great shape of the story, a hot, dense beginning, a long cooling, the slow assembly of galaxies and stars and heavy elements, and eventually, listeners, stands on too many independent legs to fall. What could genuinely shift, if the model is revised, is some of the fine print. And I will be honest, even here, in the softest chapter of the night, the universe's age, for instance, currently inferred to be about 13.8 billion years, is calculated within the standard model. And if the model changes, estimates of its precise age could shift too. Not the childhood photograph, but the caption beneath it. Every observation we have shared tonight was real and stays real. Only the deep wiring diagram behind the observations is under renovation. The house is not being demolished. The house is getting better blueprints. There is a habit of mind in all this worth taking with you past tonight. And it might be the most practical gift this story has to offer. Notice that the people closest to the puzzle are the calmest people in it. Riess calls the possibility exciting. Freedman promises the field will get to the bottom of it. Gross says crisis with something close to appetite. The people who understand the situation best are not frightened because they know what the fear gets wrong. The universe was never obligated to match our model. The model was always a map, and the territory was always in charge. When a map fails, the territory has not become dangerous. It has become, briefly and wonderfully, unmapped. So, if you carry one image out of this chapter, let it be this. Somewhere tonight, in the deep reaches between the galaxy clusters, space is stretching in a way our equations may not fully capture. And also tonight, the moon is exactly where the almanac says. Both things are true. They live at different scales, and the scale you live at is the well-behaved one. You reside in the most predictable corner of a surprising universe, on solid ground, under faithful stars, wrapped in physics that has never once let you fall, which leaves only one question. Really? And it is not a question about the sky. It is a question about us. Why should any of this feel like it matters? Here, on the shore, so far from the strange deep water, why does a small disagreement between two numbers tug at something in the chest? I think it has to do with when we happen to be alive. Come. The night is late, and this is the second to last thing I want to show you. Consider, for a slow moment, all the human beings who ever fell asleep under the stars. For almost the whole of our species' time on Earth, the night sky was a ceiling, beautiful, sacred, storied, but closed. A shepherd 4,000 years ago saw very nearly the same stars you can see tonight, and had no way, none at all, to know what a single one of them was. The questions existed. The questions are probably older than language. What is all this? How big is it? How did it begin? But for 100,000 years, the questions simply hung there, passed from generation to generation like heirlooms nobody could open. Now consider the sliver of time you happen to occupy. Within the span of a single long human life, our species photographed the infant universe, inferred its age to remarkable precision within the standard model, discovered that its expansion is accelerating, and built a golden-eyed telescope that can watch the first galaxies switching on. A child born the year Penzias and Wilson heard the Hiss could have watched. In her own lifetime, cosmology transformed from near philosophy into precision measurement. And then, in her retirement, watch that very precision uncover the puzzle we have followed all night. Nearly everything humanity has definitively learned about the cosmos as you did not miss the age of discovery. You are lying in the middle of it. And you happen to be alive for one of its most interesting stretches in decades. A moment when a highly successful model is being tested with unusual precision, and creaking in a way its keepers can hear. Think how rare that is. For long stretches, science is consolidation, filling in decimals, tidying corners, and those stretches can last generations. The last time cosmology's foundations were questioned this openly, with its finest minds saying words like crisis in public, you would have to look back roughly a century, to the decades when Mercury's orbit and the glowing coals were quietly refusing to behave. The people alive then did not know they were living near a hinge of history. We, rather unusually, get to suspect it, even if we cannot yet be sure the hinge will turn. There is also something worth savouring in how this particular puzzle was found, because it says something hopeful about our species at a moment when hope can use the exercise. This crack was not discovered by a lone genius in a locked room. It was assembled, over a century, by a chain of people who mostly never met. A hearing-impaired computer in Cambridge, earning 30 cents an hour, finding a pattern in blinking stars. A quiet spectroscopist in Arizona, clocking the flight of spiral nebulae. A Belgian priest with Einstein's equations in his briefcase. 2 radio engineers evicting pigeons from a horn in New Jersey. Satellite teams on 2 continents, mapping a baby picture pixel by pixel. A graduate student in Berkeley finding a negative number that would not go away. Thousands of engineers folding a mirror like origami and throwing it 1,000,000 miles. And rival teams, who genuinely disagree, publishing their disagreements in the open, checking each other's arithmetic across decades. The puzzle was found by cooperation so vast and so patient that no single participant could see the whole of it. Whatever else our species gets wrong, and it gets plenty wrong, this thing, this slow, honest collective reaching toward the true, is something we do that nothing else on earth has ever done. And you are part of it, in a quiet way, simply by being someone who wants to know. Science does not run on laboratories alone. It runs on a civilization that finds these questions worth asking, worth funding, worth telling stories about at bedtime. Every person who looks up and wonders is part of the reason the telescopes exist. Tonight, you gave a few hours of your rest to the honest, unfinished map of everything. That is not a small thing. That is the oldest human tradition there is. Continued. Here is the last thought of this chapter, and it is the one I would choose, if I could choose, to be the thought dissolving in your mind as sleep comes closer. We do not know how this story ends. Nobody does. Not Riess. Not Freedman. Not the theorists with their gallery of suspects. The tension may dissolve into some subtle systematic error, and that would be a triumph of care. It may crack open into new physics, and that would be a triumph of discovery. The coming years of data from Webb, from DESI, from new observatories already flying and building, are widely expected to narrow the answer, and it is entirely possible that people alive today, perhaps you, will hear the news that the 2 clocks finally agree, and will be among the few on Earth who actually know what that sentence means. And remember the whole long story behind it. The glass plates, the pigeons, the golden mirrors, told once, slowly, in the dark. Until then, the question stays open, and an open question, for a mind settling towards sleep, is not an itch. It is a horizon. The horizon is close now. One last walk down the hallway, and we can say good night. So here we are, back where the night began. The long wooden hallway, the still air, the two clocks on their opposite walls, each one built by a century of devoted hands, each one telling a slightly different time. You know them now. You know what they are made of. One is built of blinking candles and exploding stars, of Henrietta Leavitt's patient eyes and Adam Riess's stubborn checking, and it measures the universe as it is tonight. And it reads 73. The other is built from the oldest light there is, the baby picture of everything, wound carefully forward through 14 billion years of mathematics. And it predicts 67. Between them, in the quiet of that hallway, hangs one of the most closely watched silences in modern science. And you know now what that silence is not. It is not a scandal. It is not a failure. It is not the sky beginning to fall. Every measurement we visited tonight was made honestly, checked relentlessly, published openly. The most doubted link in the ladder was handed to the sharpest telescope our species has flown. And the suspected error was not there. The silence between the clocks is simply the sound of a question that has finished forming and has not yet met its answer. It may yet be a question about instruments. Some subtle bolt, still loose in a rung, nobody has thought to shake. It may be a question about the universe itself. Science has heard silences like this before. Above a misbehaving planet, inside a glowing coal, and sometimes, not always, but sometimes, on the far side of the silence, the universe turned out to be larger and stranger than the model it had outgrown. Maybe that is why this story belongs to the night. Because falling asleep is itself a small act of trust in an unfinished world. You do not know everything tomorrow holds, and you close your eyes anyway. The cosmologists do not know what the two clocks mean, and they keep measuring anyway. And then they go home, and they sleep too. Certainty was never the price of rest. If it were, no one would ever have slept at all. So let the images of the night drift past you now, one last time, unhurried, in no particular order, asking nothing of you. A woman at a wooden desk in Cambridge, a century ago, bent over a glass plate scattered with stars, noticing that the bright ones blink slowly. A young man in California, staring at a negative number, checking it again, and feeling the floor of the universe tilt gently beneath him. Two engineers in New Jersey, scrubbing a giant horn in the cold, unaware that the noise they cannot remove is the light of the universe's first morning. Arriving on schedule, a golden mirror, folded like a sleeping moth, riding fire into the dark on Christmas morning, then opening, petal by petal, 1,000,000 miles from home, in silence, perfectly, and light, always light. In every part of this story, light stretched by the growing universe, light bent around galaxies, light from candles and flashbulbs and the fog lifting at the beginning of time, all of it travelling patiently across the ages to end its journey in a telescope, or in an equation, or here, tonight, in a dark room, in the mind of someone almost asleep. The universe is expanding as you lie there, and, in the nearby cosmos, as best we can measure it, the expansion runs faster than the standard model, calibrated on the early universe, predicts, somewhere beyond the last galaxy your eyes could ever find. Space itself is stretching, calm and enormous and unhurried, exactly as it was doing before you were born. exactly as it will be doing tomorrow, whether or not we ever learn its reasons. It does not need our understanding in order to carry on. It never has. Our understanding is a gift we give ourselves, one careful measurement at a time. And it can wait for morning. You do not need to hold any of this anymore. The numbers can go 67, 73. Let them drift off first. The suspects in their gallery can dim their portraits. The hallway can keep its own counsel until you visit again. Everything you learn tonight will keep. It is written in journals and carved into data, and the people who guard it are careful, and the telescopes are watching even now, gathering photons in the dark on your behalf, so that nothing true is lost while you rest. Somewhere, a Cepheid is brightening, right on time. Somewhere, the oldest light is arriving, as it always does. The 2 clocks are ticking in the hallway, patient as ever, keeping their beautiful disagreements safe until someone, someday, understands. It does not have to be tonight. Nothing has to be tonight. Let your breath grow long and slow. Let the question rest on the pillow beside you, not as a worry, but as a companion, the way the sky has always been a companion, unanswered and faithful, above every sleeping generation there has ever been. The universe is stranger than we knew, and you are safely inside it. Good night,